Hello and welcome to Math Zone African Motives. Today, we're diving into a very important topic, inverse trigonometric functions. By the end of this video, you will be able to define inverse functions, write their notation correctly, and most importantly, differentiate the 6 inverse trigonometric functions. First, let's refresh our memory from N4. What is an inverse function? An inverse function, which we denote f inverse of x, essentially reverses or undoes the action of the original function. Think of it like putting on and taking off your shoes. Putting them on is a function, and taking them off is its inverse. The key principle is that the input and output values swap places. So, if f of x equals y, then its inverse, f inverse of y, equals x. To find the equation of an inverse function, you simply interchange the x and y variables in the original equation. Let's quickly look at a linear example to solidify this idea before we move to trigonometry. Consider the function y equals 2x plus 3. To find its inverse, we first interchange x and y, which gives us x equals 2y plus 3. Our goal is to write the inverse in the standard form, y in terms of x. So we rearrange this equation to solve for the new y. We subtract 3 from both sides to get 2y equals x minus 3, and then divide by 2 to get y equals the quantity x minus 3 over 2. This is the inverse function. So we've gone from the function f of x equals 2x plus 3 to its inverse, f inverse of x equals x minus 3 over 2. Now what happens when we try this with trigonometric functions? Let's take the function y equals sin of x. If we follow the same process, we swap x and y to get x equals sin of y. The problem is, we can't algebraically isolate y in terms of x using standard operations. We need a new way of writing the inverse action. This leads us to the notation for inverse trigonometric functions. We write y equals sin inverse of x, or sometimes y equals arcsine of x. These two notations, sin inverse of x and arcsine of x, mean exactly the same thing. You'll typically find the sin inverse button on your calculator. Similarly, we have inverse functions for all 6 trigonometric ratios. These are cosine inverse, tangent inverse, secant inverse, cosecant inverse, and cotangent inverse. They all follow the same principle of reversing the original trigonometric function. There are 2 critical points to understand about this notation. This is very important for your exams. Firstly, ei equals sin inverse of x is just notation for the inverse function. It does not, it does not mean 1 over sin of x. Let's be very clear. The L1 here is part of the function's name. It's not an exponent. If you wanted to write the reciprocal of sin of x, you would write the quantity sin of x, all raised to the power of -1, or its reciprocal, which is cosecant of x. So, sin x to the power of 1 is the reciprocal of sin x, or 1 over sin x. This is cosec x. They are different. Let's be absolutely clear. The y1 in sin inverse of x indicates an inverse function. The y1 in sin x to the power of 1 indicates a reciprocal. Because inverse functions undo each other, they have some powerful properties when you compose them. Let's see them. The property is that a trigonometric function of its own inverse is simply x. For example, sin of sin inverse of x equals x. Similarly, cos of cos inverse of x is x, and tan of tan inverse of x is also x. Let's quickly prove the first one. This is a common and important step to understand. We want to prove that sin of sin inverse of x equals x. The standard proof method is to let y equal the inner function, sin inverse of x. By the definition of an inverse function, this means that x equals sin of y. Now let's take our original expression, sin of sin inverse of x. We can replace sin inverse of x with our variable y, so it becomes sin of y. And from our definition, we know that sin of y is equal to x. So we've proved that sin of sin inverse of x equals x. We just used the definition of an inverse function. Now we arrive at the core of today's lesson, differentiation of inverse trigonometric functions. It's time to learn how to find the derivatives of these functions. There are 6 formulae for the derivatives of the inverse trigonometric functions. Before we apply them, it's very important to understand where they come from. Understanding the derivation of these 6 differentiation formulae is an important skill and a common question in examinations. So pay close attention to this process. Let's start with the first one. The derivative of y equals sin inverse of x. We will use the technique of implicit differentiation. First, by definition of the inverse function, y equals sin inverse of x is equivalent to writing x equals sin of y. Next, we differentiate both sides of this equation with respect to x. Differentiating x with respect to x is just 1. Differentiating sin of y with respect to x requires the chain rule. The derivative of sin is cos, so we get cos of y. And because we're differentiating with respect to x, we must multiply by the derivative of the inner function y with respect to x, which is di x. Rearranging this equation to solve for di d, we get that di dx is equal to 1 over cos of y. Now we have a derivative in terms of y, but we want it in terms of the original variable x. To do this, we'll use a fundamental trigonometric identity. The identity is sin squared of y plus cos squared of y equals 1. We can rearrange this to solve for cos of y, which is the square root of 1 minus sin squared of y. For the purposes of the standard inverse function, we take the positive root. This gives us di slash dx equals 1 over the square root of 1 minus sin squared of y. Remember, from the beginning, we established that sin of y equals x. So, we can substitute x in for sin of y. This gives us our final powerful formula. The derivative of sin inverse of x is 1 over the square root of 1 minus x squared. This is a formula you must know. Now that we've derived the first one, let's list all 6 differentiation formulae. These are the tools we will use to solve problems. We just derived that the derivative of sin inverse of x is 1 over the square root of 1 minus x squared. The derivative of cos inverse of x is almost identical, but with a negative sign. Negative 1 over the square root of 1 minus x squared. Next, the derivative of tan inverse of x is 1 over 1 plus x squared. This one is particularly clean. And similar to sin and cosec, the derivative of cot inverse of x is the same as tan inverse of x, but negative. It's negative 1 over 1 plus x squared. The last two have a slightly more complex form. The derivative of sec inverse of x is 1 over the absolute value of x times the square root of x squared minus 1. And finally, the derivative of cosec inverse of x is the negative of the derivative of sec inverse. It's negative 1 over the absolute value of x times the square root of x squared minus 1. It's easy to see the pattern here. The derivatives of the co-functions, cos, cote, cosec, are the negative versions of their non-cofunction counterparts, sin, tan, sec. These 6 formulae are the tools we'll be using for the rest of the examples. Make sure you have them written down. Most of the time, the argument of the inverse trig function won't just be x. It will be some other function of x. This is where the chain rule comes in. Let's derive a general formula for the chain rule application. If we have a function y equals sin inverse of f of x, where f of x is any differentiable function of x, using the chain rule, the derivative of y with respect to x di x is the derivative of the outer function evaluated at the inner function, multiplied by the derivative of the inner function. The derivative of the outer function, sin inverse, is 1 over the square root of 1 minus. But instead of x squared, we have f of x, so it's f of x all squared. Then we multiply this by the derivative of the inner function, which is f prime of x. So our final general formula is di slash x equals f prime of x over the square root of 1 minus the quantity f of x squared. This pattern holds for all 6 inverse trigonometric functions. The general form is the derivative of the argument in the numerator, divided by the derivative of the inverse function evaluated at the argument. Okay, enough theory. It's time to apply these formulae to some examples. We're going to differentiate the following problems. Let's start with number 1. Y equals cos inverse of cot ix. This looks like we might be able to simplify it first. Cos inverse and cos are inverse operations. If we could simplify it to y equals x, the derivative would be 1. Let's see if that's the case. Without simplification, we would use the chain rule with the cos inverse formula. Here, our inner function, f of x, is cos x. The derivative of our inner function, f prime of x, is negative sin x. Now we apply our general formula for cos inverse of f of x, which is negative f prime of x over the square root of 1 minus f of x squared. Plugging in our values, we get negative sin x in the numerator, and in the denominator, we have the square root of 1 minus cos squared of x. This simplifies to sin x over the square root of sin squared of x, which is sin x over sin x. The result is 1. This confirms our intuition. The simplification was valid, and we got 1. The key takeaway is that even if you can simplify, understanding the chain rule is crucial for problems where you can't. Let's move to the next example. Number 2 is y equals sin x times sin inverse of x. Here we have a product of two functions. U equals sin x, and v equals sin inverse of x. Therefore, we must use the product rule. The product rule states that the derivative is u prime times v plus u times v prime. First, let's identify u and v. The derivative of u prime is cos x. The derivative of v prime is the formula for the derivative of sin inverse of x. Now, we just plug these into the product rule formula. dx equals cos x times sin inverse of x plus sin x times 1 over the square root of 1 minus x squared. We can rewrite this for clarity as cos x times sin inverse of x plus sin x over the square root of 1 minus x squared. This is our final answer. Let's tackle number 3. Y equals the natural logarithm of tan inverse of x cubed. This problem requires multiple chain rules. It's a composition of three functions, the natural log, tan inverse, and x cubed. The overall function is a natural log, ln of fx, where our inner function fx is the entire tan inverse of x cubed. The derivative of ln of fx is f prime of x over f of x. So we'll need to find the derivative of our inner function, tan inverse of x cubed. To find this derivative, we use the tan inverse chain rule. Let g of x equal x cubed. Then g prime of x is 3x squared. The derivative of tan inverse of x cubed is 1 over 1 plus x cubed squared times 3x squared. This simplifies to 3x squared over 1 plus x to the power of 6. This is our f prime of x. Now we can put it all together. Dx is f prime of x, which is our 3x squared over 1 plus x to the 6th. All divided by f of x, which is tan inverse of x cubed. This is our complete derivative. Let's look at number 4. Y equals tan inverse of the natural logarithm of x. This is a composition of two functions. Tan inverse of fx, where fx is ln x. Our inner function is f of x equals ln x. The derivative of this inner function, f prime of x, is 1 over x. We apply the general formula for tan inverse of f of x, which is f prime of x over 1 plus f of x squared. Substituting our values, we get dx equals 1 over x divided by 1 plus ln x squared. This is our final derivative. Our final and most complex example is number 5, phi. Y equals cos inverse of x divided by the square root of 1 minus x squared. Because this is a fraction, the first rule we must apply is the quotient rule. The quotient rule is v prime minus uv prime, all divided by v squared. Our numerator is u equals cos inverse of x, and its derivative u prime is negative 1 over the square root of 1 minus x squared. Our denominator is v equals the square root of 1 minus x squared. It's often easier to write this with a fractional exponent, 1x squared, to the power of 1/2. We need to use the chain rule to find v prime. V prime is 1/2 times the quantity 1 minus x squared to the negative 1/2 power, multiplied by the derivative of the inner function, negative 2x. The 2's cancel, and we can move the negative 1/2 power to the denominator as a square root. So, v prime is negative x over the square root of 1 minus x squared. Now we have all the pieces. Let's substitute them into the quotient rule. Dx equals v times u prime, which is the square root of 1 minus x squared times negative 1 over the square root of 1 minus x squared, minus u times v prime, which is cos inverse of x times negative x over the square root of 1 minus x squared, all divided by v squared, which is 1 minus x squared. Now we just need to simplify this expression. In the numerator, the square root terms cancel out to -1. The negative signs in the second term multiply to a positive. We then find a common denominator for the numerator's terms and divide by the denominator. After multiplying top and bottom by the common denominator and simplifying, we arrive at our final answer. Let's pause here and verify our final answers. By comparing with the provided solutions, we can confirm our work. All of our answers match the solutions, verified using memo. Let's quickly recap what we've learned today. We started by understanding that inverse functions reverse the action of another function, and we denote them with a 1 in the superscript. We distinguished between inverse functions and reciprocals, emphasizing that sin inverse of x is not the same as cosecant of x. We saw the powerful composition properties of inverse functions and then dived into the main event, differentiating the inverse trigonometric functions. We saw the derivation for sin inverse of x and listed all 6 formulae. Finally, we applied these formulae in a series of examples using the chain rule, product rule, and quotient rule in conjunction with the inverse trig differentiation rules. A key takeaway is that when the argument is a function of x, you must use the chain rule. Thank you for watching. Mastering these concepts is a critical step in your calculus journey. Make sure to practice these derivations and applications. For more tutorials like this, subscribe to Math Zone African Motives.